Welcome! In this series of short videos, we will look at topics common to both the PowerBasic console and Windows compilers. Today we will look again at the use of the matrix command to solve linear equations. Today we're going to be looking at solving linear equations using PowerBasic's inbuilt matrix command, the mat command. We have some linear equations showing on screen here, and our task is to figure out the values of the x, y and z variables, or z as our American colleagues would call it. As we're going to be using the mat command, we're going to have to declare some arrays. Each of these arrays will represent one matrix. First of all, we're going to set up a matrix to hold the coefficients. As we have three equations here, and we have three values to find out, this needs to be a matrix array which is 3 rows by 3 columns. We're declaring this as an extended precision array. When dealing with decimal points in numbers, we have several choices in PowerBasic. We can pick a single precision, double precision, or extended precision. The extended precision floating point variable type gives you 18 digits of precision, and each of these variables takes 10 bytes of storage. This allows you the most precision allowable inside PowerBasic for floating point numbers. So all the arrays we're going to create today will be set up as extended precision. So next we can look at initializing the values inside our coefficient matrix. And we will do this row by row, column by column. First of all, we will handle the first row. The first row is 2x plus y minus z equals 7. The first value we'll put in is the 2. The next value, in this case, is effectively 1y, so we will put in 1. And the final value, since this is being subtracted, this will be a negative value. And as there is no number in front of the z, we will make it minus 1. So this populates the first row of our coefficient matrix. We will then do exactly the same for each of the other rows. So we now have row 1, row 2 and row 3 all populated with their values. As you can see from the last row, the first value is 1, the next value is plus 3, and the next value is plus 2. Should any of these have been minus here, the figure would have been minus in the array. As such, we only have one minus figure in our array. So now that we've populated this coefficient matrix, the next thing to work out is our constant vector matrix. This is going to hold 3 values. These will be the values in the right-hand side of our equation. These are known values. So we're setting the values to 7, 17 and 11, which equates to what's on the right-hand side of our equation. Before we go further, for the purposes of documentation and to allow this to be easily seen on screen, we're going to create a small function whose job it will be to print out these matrices. So we will need 2 different functions, one to print out a 2-dimensional matrix, our coefficient matrix, and one to print out our single dimension matrix, which is our constant vector matrix. So let's now go and create these 2 functions. Here is the skeleton of our first new function, taking 2 parameters, a by reference pointer to our matrix array, and the second parameter is the name we wish to display on screen. So we have declared 2 local variables, one for row and one for column. First, we'll change the colour on screen to allow the name of the matrix to be a different colour from the actual text. We're using all the commands that exist within the console compiler just for convenience. Next, we need a nested for next loop. The outer loop is going to be for our rows, and the inner loop will be for our columns. We're using the ubound command to work out the maximum size of our array. The ubound command has a second optional parameter. For the row, we're using a comma 1, which means we're talking about the first dimension. For the column, we're using comma 2 in the ubound command, which means we're interested in the second dimension. So all we need to do now is to print out the value contained within this matrix by row and column. And we're using the semicolon at the end of the line to ensure that PowerBasic does not do a carriage return line feed until we have finished the whole row. And we're going to do a square bracket at the beginning of a row and a closing square bracket at the end of the row, with no semicolon at the end, which means PowerBasic will then insert a carriage return line feed. And we will put a print command at the very end of the function to ensure we have a blank line between this array, display, and whatever is going to appear next. We will now create the one-dimensional matrix, which, since it only has one dimension, we only need to handle the row. So the nested loop is no longer required. We have a single for next loop, doing exactly the same as we did before, putting an opening square bracket at the beginning and a closing square bracket at the end to indicate what we're printing on screen is in fact a matrix. So if we try running the application now, just to see what we're going to get on screen. And there we have our linear equations at the top of the screen, followed by our coefficient matrix and our constant vector matrix. So we can see at a glance what has been put into each of these two matrices. So now that we have these populated and displayed on the screen, the next thing we want to do is to calculate the determinant. This is for error checking. A determinant can only be calculated for square matrices. That is a matrix with the same number of rows and columns. So we're going to run this on our coefficient matrix. As you can see from the calculation, which is stepping through each of the cells within our matrix, we're going to end up with one number, which we're calling the determinant. We can use this to determine whether the matrix is singular or not. This will allow us to determine whether the matrix does actually have an inverse. In order to work out the value of our x, y, and z variables, we're going to have to invert the first coefficient matrix. So we can test the value of our determinant by using the ABS command. If this is less than 1e to the minus 6, then we can print a message out to say the matrix is singular and has no inverse. There are, of course, other ways to work out this error. Next, we need to work out the inverse of our coefficient matrix. PowerBasic makes this very easy to do by using the mat command. We will, of course, need another array matrix to store this inverse set of values. And we're going to call that array ext inverse. And again, it has to be the same size as the matrix we are inverting, in this case 3 rows and 3 columns. While we're here, we can declare our determinant value, again as an extended precision value. And there is one other matrix we'll need to dimension here, and that is the solution, the 3-row matrix that's going to hold the values of x, y, and z. And we'll call that one basically solution. So now that we have all our matrices set up, we can now go ahead and do the calculation. So as I said, first we will calculate the inverse of our coefficient matrix. And PowerBasic makes this really easy by using the invert command inside the mat command. That will populate our inverse values. So now that we've got those populated, we can call our two-dimensional print to see what values it has calculated. So here we are ready to call our print two-dimensional matrix, giving it the inverse matrix to process. If we run that now, we can now see the values in our inverse matrix. In order to get our solution, we now have to multiply the inverse of our coefficient matrix, the one we have just calculated, by the constant matrix to get the solution, and we can populate the solution matrix with those details. And again, PowerBasic makes this easy by giving us the mat command to populate the solution matrix by multiplying the inverse matrix by the constant matrix. So now that we have populated our solution matrix, we can now display this on screen by simply printing out the value in each of these rows. And there we have, at the bottom of the screen, our solution. X equals 3, Y equals 2, and Z equals 1. We can, of course, optionally verify our result by multiplying the coefficient matrix by our solution matrix, and this should give us a check. So let us dimension yet another array, and we'll call this one check. This one is only going to have 3 rows. So multiplying the coefficient matrix by the solution should get us back to where we started. So now that we've performed that, let's now print out this one-dimensional array and run our application once more. So here we have our verification, which gives us 7, 17 and 11, which are the values we had in the constant vector matrix. The fact that these two match exactly tells us that our solution is in fact correct and has been verified. So in summary, what we've done today is we've taken 3 linear equations, we've generated a coefficient matrix, and a constant vector matrix. We have calculated using the mat command the inverse of our coefficient matrix, and we have obtained a solution. We have then verified that solution by multiplying the coefficient by the solution to give us a constant. These constants match the constants we had originally. So PowerBasic gives you some very powerful matrix processing commands. Hopefully you'll find these useful in your own applications, but that's it for today. Thank you for watching.